All right, this is good. Okay, so for those of you watching it online, I have to talk into this blue thing, otherwise none of you will hear me, but that's okay. So today we'll be talking about model-based reinforcement learning. A few quick notes. Homework 3 is out. We'll check the due date. I think it's due next week, but someone just told me that we'll post it on Gradescope that it's the week after. We'll confirm that and we'll post it on Piazza. But either way, make sure that you start earlier on this. It takes a little while to run the Atari part of the Homework 3 especially. Today's lecture. Today we're going to cover the basics of model-based reinforcement learning. One can crudely characterize the basics of model-based reinforcement learning as simply being learn a model and then use that model for control. But this very straightforward kind of naive approach often doesn't work very well. So we'll find out a little bit why, and we'll discuss how we can make it work better. We'll then talk about the effect of distributional shift in model-based RL and how we can mitigate that. And we'll talk about uncertainty in model-based RL and how in model-based RL especially it's very important to learn models that are aware of what they don't know. Then we'll, in the second half of today's lecture after the break, we'll talk about model-based RL with complex observation spaces, like images. And then next time, on Wednesday, we'll talk about how we can do model-based RL with policy learning. So today, all of the methods that I'll discuss are kind of in that open-loop planning regime, and then on Wednesday, we'll come back to policy learning. So the goals for today's lecture will be to understand how to build model-based RL algorithms, understand the important considerations for model-based RL, how to design good model classes, how to estimate uncertainty, and so on, and understand the trade-offs between different model class choices. All right, so why should we think about learning a model? Well, if we knew this f of st comma at, we could use the tools from last week to actually plan through that model and make decisions. And we saw at the end of last week's lecture that if you actually have a ground truth model, you can do some pretty impressive stuff. So if we could only acquire a model that is sort of comparably good to the true model, then we could get some really interesting behaviors to emerge. And of course, this is sort of in the deterministic case. In the stochastic case, you could imagine that you estimate the probability of the next state given the current state in action. So let's try to think about learning f of st at from data, and then use that learned model to plan through it to actually take useful actions in the world. So from this, we can kind of write out the model-based reinforcement learning algorithm version 0.5. And I call it 0.5 because it's sort of questionable as to how well this would actually work in practice, but this is our first kind of baby version of a reinforcement model-based RL algorithm. Step 1, you run some kind of base policy, we'll call it pi0, to collect a data set. And it's a data set of transitions. It's a data set of tuples S, A, S prime. Then we're going to use these tuples to learn a dynamics model, and you could learn a deterministic model or a stochastic model. So here I have it written out in a form that maybe makes sense for a continuous state deterministic model, so you minimize maybe the squared error between the model predictions and the true next state. If you have a discrete state, maybe you use something like a cross-entropy loss. You could also have some stochastic model with some arbitrary parameterized distribution, and that would change the form of that loss function. So that loss function at the end, in general, this thing would be some kind of maximum likelihood thing. So once you've learned the model, step 3 is plan through this model to choose your actions. And if you've got a good model, then step 3 should work well, maybe even as good as the thing that we saw last week. So does this actually work? Well, yes. In some cases, it actually works decently well. This is essentially how system identification works in classical robotics. So if you have a kind of a background in engineering or robotics and you've heard the term system identification basically follows this recipe. You run some base policy, you collect some data, you fit the parameters of your model, and then you use that model. Now, some care needs to be taken to design a good base policy. So if your base policy just sort of sits there and does nothing, then you probably won't actually collect data that is useful for identifying a good model. And this kind of thing is particularly effective if you can hand engineer your dynamics representation, your model class F, using your knowledge about how the system really works. So this kind of stuff can work well if, for example, you know that you're controlling a robotic arm with 7 links and revolute joints, and all you need to know is how heavy each link is. So if you have a small set of physical parameters, this kind of 0.5 version of the method is a decent way to get an estimate for the value of those parameters. But if you're training a very complex dynamics model, like a deep neural net, this tends to work somewhat poorly. And that's what we're going to try to understand on the next slide. So this is here we're going to sort of confront one of the most basic issues with model-based reinforcement learning. Let's say that my task is to get my agent to climb to the peak of this mountain. And step 1 in my model-based RL version 0.5 algorithm is to run my base policy, which could be some kind of random policy, to collect some data that I can use to train my model. So maybe this is what my base policy does. It goes for a little random walk on the slope of this mountain. Now, if I use that data to fit my model F, my model will probably tell me something like, you know, the further to the right you go, the higher you are, right? So the peak is somewhere to the right. So if you go to the right, you'll get higher up on the mountain. So just go right, right? That's kind of a reasonable thing to conclude from the data collected along those red paths. So then if I take that model to be essentially the truth, and then use it to plan a path that maximizes my reward, that's step 3, I'll probably end up doing something like this. So what really happened here? I mean, maybe the obvious answer is that, well, my model wasn't really a good model. I thought it was better than it really was, and as a result, it led me astray. But more mathematically, this is actually an issue that we've seen before. The issue is that we have some kind of function approximator, in this case f. It was trained on a particular data distribution, and then we used it to extrapolate beyond that data distribution in ways that were kind of unjustified. So the training data, the training states, came from the distribution p pi 0 of s. When we then go to actually control our system to reach the desired goal, we're going to go to different states. Let's say that pi f is the policy induced by planning through f. Then the states that we visit come from some other distribution p pi f of s. And that other distribution is very, very different from the one that collected the data. So that means that our policy, the implicit policy, the one induced by planning through f, ends up trying to act in states that are very, very different from the ones in which the function approximator f was trained, and therefore f isn't really making reasonable estimates from those states. So we've seen this problem before. We saw it when we talked about imitation learning. And we even saw something like a solution to this problem. So does anyone have any suggestions about how we can address this issue for model-based reinforcement learning? Yes, back there.
Maybe do something kind of like Dagger and then go back and collect some more data?
Right, so you could do something, the answer was you could do something like Dagger and you could go back and collect some more data. So let's try to imagine an algorithm that actually does that. So this is a distribution mismatch problem, and it becomes actually exacerbated as we use more expressive model classes because they can fit the training distribution better and extrapolate worse. So can we make p pi 0 of s be equal to p pi f of s? So let's borrow the lesson we learned from Dagger. So we're going to run our base policy pi 0 to collect our initial data set. We'll use that initial data set to learn a dynamics model f. Then we'll plan through f to choose actions. And then we'll execute those actions and add the resulting data back to our data set. So we'll actually, just like in Dagger, we aggregate the data. Here we also aggregate the data. Now in Dagger, remember, we needed to get our data labeled with the ground truth function. For imitation learning, the ground truth function was the true policy. Here we're not learning the policy, we're learning the model. So the true function is the true model. When we execute those actions in step 4 and we add additional data from the real world to our data set, we are in effect labeling the SA tuples with the true S prime. So this is essentially implementing Dagger, but for models rather than policies. And then of course we repeat this process, and if we repeat it often enough, eventually the model F stops changing, and at that point we're actually collecting data from P pi F. So that will address this distributional shift problem. So where have we seen that before? Well, we saw it before in imitation learning. So I call this model-based reinforcement learning version 1.0 because this is kind of the first class of model-based reinforcement learning algorithms that actually kind of has a chance of working in the deep RL regime with high-capacity function approximators. Now there's a little bit of a detail and a little modification to this method that can actually make it work quite a bit better. The current method, as I described here, should in principle work and converge decently well, but it might take quite a while to get there because you need a pretty good model if you want to plan through it and then execute a big long trajectory. So you can do a little bit better. Let's imagine that you're not doing this hill climbing thing, but instead you're driving a car. And you make a little small mistake. So maybe your model is a little bit incorrect and your model says, the car will go straight if you turn the steering wheel a little tiny bit to the left. It's a small innocuous mistake, so you'll turn the steering wheel a little bit to the left because you want the car to go straight. But now the car is not going straight anymore. And now you're in a slightly different state. And you'll probably turn the steering wheel a little bit more to the left to compensate. But that's, of course, the wrong thing to do. And eventually you'll get off the road. Now, if you run that model-based RL version 1.0 algorithm, you will actually try doing this, append the resulting data, and hopefully get a better model. But you'll never get a model that's truly perfect. It might take you a very long time to get a model that is good enough such that these mistakes don't really compound. So you can actually address this issue decently well, even if your model is highly imperfect. Does anybody have any ideas about how to do that? So let's say that our model is imperfect, but generally has a reasonable idea. So it says, you'll go straight if you turn the steering wheel a little bit to the left.
Do a look ahead?
Do a look ahead? What does that mean?
Look a certain number of steps ahead, and then pick the one action for the trajectory that maximizes your reward.
Okay, so you could, for example, plan into the future, pick one action from that plan, execute that one action, and maybe you could try planning again. So a reasonable strategy to take here is instead of just generating your plan to steer the car to drive along the road and then going and blindly executing that plan, what if you keep an eye out for what's actually happening, and if what's happening deviates from what you had expected, just try to replan again and see if you can correct that mistake. So maybe if you did what your model told you and steered the car a little to the left, now you're not going straight anymore. Well, once your mistake becomes big enough, if your model is kind of decent, it should eventually tell you that you should correct by steering back to the right. If you had just blindly followed your plan, then you wouldn't have realized this, but if you replan from the state that you actually reached, rather than assuming that your model would be correct, then you might still have a chance to fix this. So this gets us model-based reinforcement learning version 1.5. You run some base policy, just like before. You learn your dynamics model. Then you plan through your dynamics model to choose a sequence of actions. But then you only execute the first planned action and observe what actually happened after you took that action. You append the transition SAS prime back to your data set. So you collect the data. And then you plan again. So you're essentially replanning every single time step. So that means that if the car deviated from the trajectory you thought it would follow, you would replan and try to correct. And if your model is not perfect but kind of okay, this can actually make the performance of this method a lot better. This is referred to as model predictive control, or MPC. So if you see someone say, oh, I'm doing model-based RL with MPC, what they mean is that they're replanning every time step. And then, of course, you have this outer loop where every, let's say, n steps, you go and retrain the model on all of your aggregated data so far. This is basically meant to help with model errors. This doesn't really change the high-level idea behind the algorithm. It just makes it so that you get better performance sooner before your model gets completely perfect. And in fact, in very complex environments, your model might never become perfect. Maybe your model is not big enough, or maybe it needs too much data. So this can actually give you pretty good performance even with highly imperfect models. And you'll actually be implementing this for homework 4. So this model-based RL version 1.5 algorithm is a pretty decent algorithm. You can actually solve a lot of really interesting problems with it. And that's what we'll be doing in our model-based RL homework, which is the next one after this. So last week on Wednesday, I actually showed you this video where the true model was used to control a bunch of little simulated robots. Actually, in that video, let me just go back to the video for a second. In that video, they also have a section where they intentionally gave it the wrong model. So here, they told the planner that the little hopping robot is half the weight that it really is. And here they told it it was double the weight that it really is. And it's not perfect, but because it's replanning every single time step, it actually does something kind of decent. So if you were to just plan in open loop and then try to execute that plan, you wouldn't get anything reasonable. But if you replan, then you can actually do decently well. And in fact, replanning compensates for imperfections in the model and imperfections in the planner so well that you don't even need to plan particularly effectively. So you could, for example, use much shorter horizons. You could use a weaker planner, like a random shooting method, instead of the kind of gradient-based thing that they're using in this video. And even just kind of, the simple random sampling methods can actually work pretty well if you replan every single time step. So to a large degree, this replanning stuff can compensate for model errors, weaknesses in the planner, and so on. Okay, so that's what was used in that video that you saw at the end of lecture last week. All right. At this point, since I've basically presented the first algorithm that you can set up that will actually work well, do any of you have any questions about this approach? And this is a good time to ask those questions because you'll all need to implement this for homework 4. Yes, back there.
It sounds expensive. Does it take a long time to
Yeah, the question is, this sounds kind of expensive. Doesn't this take a really long time? It does. So, in fact, in homework 4, you'll find out just how expensive it is. And that's actually part of the reason why we might actually prefer planning algorithms for step 3 that are not as good in terms of producing excellent plans, but are more efficient or easier to parallelize. So, for example, the random shooting method that I presented last week is really a terrible optimization method. But if you have a GPU and can run a bunch of rollouts in parallel, it can be a lot faster in terms of total time needed to compute a plan than, for example, the fancy gradient-based optimizer that is used to make this video. Yes, here?
Don't you introduce correlation between the observations when you're trying to do the least squares part? Because they're not IID, right? The samples.
Right, so the question was about step 2 in this algorithm. Aren't you introducing some correlations when you're collecting data and then running step 2? So to be perfectly clear, in step 2, we minimize the error or maximize the likelihood on all of the data seen so far. So in a practical implementation, step 5 would append your data to a big buffer, and then step 2 would do like an entire run of mini-batch SGD on the whole buffer. So if your buffer is big enough, every step of that mini-batch SGD would be decorrelated. So you're not actually updating your model online with every single transition you see. You're just adding the transitions to the buffer, just like in the Q-learning, deep Q-learning discussion we had before. And then when you actually run training, you sample IID from that buffer. Back there?
What did you mean by even random sampling can often work well?
So this is the most basic algorithm that we discussed last week, which is sample random sequences of actions and take the best one. It's not a bad optimization algorithm. Actually, it's a very bad optimization algorithm, but it's very fast. Any other questions? Yes?
Can you use cross-entropy method also?
Can you use cross-entropy method also? Yes, you can use cross-entropy method. You can use CMAES. You can use pretty much anything. The question is how do you want to strike that trade-off between computation cost versus getting this thing to actually run at something resembling real time. All right. So we discussed a method for doing model-based RL. Let's talk about how well it works. So this is a plot from a paper by Anusha Nagabandi, who conveniently enough is one of the TAs this semester. So if you have any issues with this plot, you can go to her office hours and ask her. But what this plot is showing is what happens when you run model-based RL, and what happens if you then run model-free RL starting from where model-based RL left off. So this is the cheetah task that some of you might remember from homework 1. This little brown part of the curve shows what happens if you run pure model-based RL, basically the method that I described on the previous slide, for about the equivalent of 10 minutes of real time. So this is if the cheetah was actually running for 10 minutes. And it goes from a reward of like close to 0 to about 500. And it pretty much kind of plateaus there. If you then run model-free RL for about 10 days, it does a lot better. It gets to a reward of above 5,000. So this is what a reward of 500 looks like. It's not terrible, like it's kind of shuffling forward a bit. And here's what 5,000 looks like. It's kind of a nice, healthy cheetah run. Okay, so what's going on here? Why is it that the model-based RL algorithm kind of improves a bit, but then seems to sort of get stuck? Any hypotheses? Does anyone have any guesses? Why doesn't this model-based RL method end up doing better? Yes?
Because it kind of got stuck in a local maximum, probably.
Okay, so perhaps something got stuck in a local maximum, like maybe the model hit a local maximum of its likelihood. That could be. Yep.
Maybe like never got to see the states that give high reward, just like I guess it's the same idea.
Yeah, maybe somehow it didn't get to see like the important states, the good states. That could be. Back there?
Whatever you use for the model is not expressive enough to capture.
Yeah, maybe Anusha didn't set up quite the right model class. That's quite the accusation. You could ask her about that on offset. I think she set up a pretty good model class, actually. But here's maybe the problem. Maybe the problem is that Anusha had to solve an impossible problem here. See, when you're over here, you have very little data. Those 10 minutes of cheetah running, yeah, it's great that you can learn in 10 minutes, but that's not very much data. So you need to use a function class that doesn't overfit when you have a very small amount of data in the beginning. But you need a function class that's also expressive enough so that it still has enough capacity to capture the true model when you're closer to this regime. It turns out to be pretty hard to do that with neural nets. It's especially hard because of how model-based RL works, because the planner in model-based RL is explicitly trying to find plans for which the model predicts a high reward. So if the model makes mistakes and erroneously predicts high reward, those are exactly the paths that the planner will select. So here's our model-based RL version 1.5 algorithm. And let's imagine that our model is quite expressive. So this is a very expressive model. In this case, this is a high-degree polynomial fitting a bunch of points. The actual points are distributed according to a linear function plus some Gaussian noise. So the black line shows the true function. But the model fit these points very, very well. And imagine for a second that what I'm plotting here is not the actual predictions from the model for the next state, but actually the predictions for the model as a function of a sequence of actions for the total reward. So the y-axis is reward. Well, it's very tempting for the planner to then select the input that will cause it to go to that peak predicted by the model, even though that peak is not real. Essentially, any mistake the model makes where it grossly overestimates the reward that it will get for some sequence of actions is a mistake that the planner could then exploit, select those actions, and produce pretty nonsensical behavior. In fact, there's a much better thing that the planner could do if it had the true model. Essentially, since the true function here just happens to be linear, the further to the right it goes, the better it will do, but that peak is all the way on the left. The peak is there because the model, in this case, is overfitted, but any model will make mistakes of some sort, and the positive mistakes will get exploited. So this is a big problem. And this problem becomes especially exacerbated in higher dimensions. So this is a one-dimensional example. And you can kind of intuitively imagine that you have this this manifold of reasonable behavior, and somewhere in that manifold there are little holes that produce mistakes, like this one, right? So this, you can kind of think of it as a hole. The higher dimensional this object is, the more opportunities there are for this function to have these holes in it where it goes outside of the region where it was trained. So in higher dimensional spaces, these kinds of screw-ups become the norm rather than the exception. And there are so many of these mistakes that even if you run additional on-policy collection, even if you keep appending more data, you might take an extremely long time to find all the mistakes, collect data for those mistakes, and fix them. And that's kind of one of the dominant hypotheses about why that learning curve on the previous slide actually saturates at 500, because there's simply too many mistakes that the model is making for this on-policy collection to catch them all and to fix them all. So perhaps what we could do is we could try to estimate whether our model is right or wrong. So these kind of mistakes, they happen in places where the model is incorrect. And the model is not just going to be wrong arbitrarily, it's going to be wrong in places where we didn't see enough data. So perhaps we can use uncertainty estimation to help detect where the model might be wrong and patch up these holes that way instead of having to collect data for every single mistake the model might make. this is an example of a function approximator. This is not a neural net. This is actually something called a Gaussian process that is providing an estimate of its uncertainty. You can do this with neural networks as well, and we'll actually discuss that shortly. But this is a Gaussian process. It's a particularly convenient but not very scalable function approximator that estimates its uncertainty. So the true function here is shown by the dotted red line. The thick red circles are the observations. And then the shaded blue region is the 95% confidence interval. So this Gaussian process is telling you that maybe close to the red dots over here, it really knows what's going on. And far from them over here, it has a very wide region of uncertainty. So it's saying, well, most likely you'll be here at the mean, but I really don't know, so you could be anywhere in that blue region. Now that is a model that is aware of its uncertainty. So imagine that we were using a model like that to solve a little navigation problem. So we're taking a walk on the shore of the ocean, and we'd like to go to this location on the cliff. So this is quite delicate because if you're not quite sure how the dynamics work, you might accidentally walk off the cliff, and then you'll be in for a bad time. So if you have fairly good confidence about where you'll end up if you try to reach that location, then maybe this is a good way to go and you'll reach the desired goal. But if you have a highly uncertain model and its uncertainty region is much wider, maybe you're better off being very careful and maybe not going right to the edge of the cliff because your uncertainty from your model tells you you have a pretty high chance of falling off if you do that, right? Because for the circle, a lot of it is off the cliff on this side. So if you can get good estimates of uncertainty, maybe your model-based planner will avoid doing those things that have a non-trivial chance of resulting in bad outcomes, and you'll kind of learn more gradually. So the expected reward under high variance prediction is very low in this case, even though the mean is the same. Now, keep in mind that all these issues having to do with model uncertainty are really just another manifestation of the distributional mismatch problem. So if we never had any distributional mismatch, of course, we wouldn't have any of these issues because then our model would only ever be tested on data from the same distribution as it was trained on. But if we have so many possible opportunities to make mistakes, the policy pi-f will actually change every single time we update our model. And we might take an extremely long time to ever converge. Okay, so the intuition behind this uncertainty-aware model-based RL method would be that in step 3, we only take actions for which we think we'll get high reward in expectation under uncertain dynamics. So this essentially prevents the planner from exploiting the model. Because if we had a single deterministic model, the planner could always discover some actions for which the model makes a mistake in the direction of the positive reward. But if we have an uncertainty-aware model, if it's a truly Bayesian model that really gives us a correct estimate of its uncertainty, then we would integrate out all those cases. And in expectation, we would actually do something reasonable. And then the model will get some more data and will adapt and so on. And eventually, the model will get low uncertainty in the good regions. And then we'll actually reach our goal. There are a few important caveats with this, though, to keep in mind. So when I showed this picture, I'm still talking about estimating the reward in expectation. There are a few things that there are a few reasons why you might not actually want to do this. So for example, you might still need some mechanism for exploring. If in expectation you're told going to the side of the cliff is a bad idea, you might stay away from that and never actually visit the interesting parts of the state space and never learn about the dynamics in that region. So you might still want to do something special for exploration if you have very delicate cases like this. The procedure I described is not doing any kind of pessimistic planning. So it's not saying, oh, don't do something if in the worst case you might get a bad outcome. You could do that also. You could have sort of a for safety critical systems, you might want intentionally a pessimistic planner that says, don't just use the expected reward of your actions, use like the lower 10th percentile or something. That's not what we're doing here, but we could. You could also imagine doing an optimistic planner. You can say, take a sequence of actions. If in the best case, if it's in the best 90th percentile, it's good. That might lead to more exploration. But again, that's not what we're doing here. So the expected value is a pretty good start. People have tried pessimistic and optimistic strategies for planning under uncertainty, and they lead to slightly different outcomes. The optimistic planners tend to explore more, but they can also get stuck constantly trying optimistic things. The pessimistic planners can be a lot safer, which is important for safety critical systems, but they might not explore enough. So it's a little bit application dependent as to whether you want to try out those things. But we'll just talk about the expected value planners for today's lecture. Okay, I haven't actually told you how to get uncertainty estimates for now, but does anybody have any questions about what I covered so far? Yes?
Are these like uncertainty estimates more important for like model-based RL than any of the model-free methods?
Right, so the question is, why am I making a big deal of this now? Is this only important for model-based RL, or could it also be important for model-free methods? The answer is, we're not entirely sure. It seems to be a really big deal for model-based RL, as in it's very hard to make them work very, very well without it. For model-free RL, things kind of seem to work without worrying about this too much. But you could imagine that, for example, in the Q-learning setting, where you also have to optimize over actions, only over one step of actions, this kind of stuff might matter. That's not what's been observed empirically so far, but it wouldn't be out of the question. Any other questions? Yes?
I still have a question about the gap thing. So here you're learning only about the P, S, A, S prime, and how do you incorporate this into your model-free part?
So the question was, how do you incorporate this into your model-free part? Sorry, which model-free part?
Like, just for Anusha's example, like how, you know, algorithmically, how did we incorporate this?
Oh, so the question is, basically, how was this plot produced? Very simple. You just take the behavior of the model-based planner, and then you run supervised learning to get a policy. And then you run policy grading from there. So very simple. It's not meant to be particularly clever. It's just meant to be something that allows you to initialize from the result of model-based RL. Any other questions? Yes?
Could you go forward? Sorry, could you go forward a couple slides? Yeah, this one. The next one, like for the caption of that. What does it mean expected reward is very low even though the mean is the same?
So the question is, on this slide, what does it mean when I say expected reward under high variance prediction is very low even though the mean is the same? So when you estimate the uncertainty under your model, the mean prediction might still tell you that your most likely outcome is to get right there to the goal on the edge of the cliff. And that's a very good outcome. So you might say the most likely outcome has extremely large reward. But if you take into account the size of this uncertainty region, then you might have some rewards there that are extremely bad for when you fall off the cliff, and your expected reward value might be lower. This is to some degree a property of the problem setting. So you could imagine environments where high uncertainty doesn't necessarily lead to bad outcomes. But in many of the tasks that we care about, there's sort of like a few things that you want to accomplish, and most other things are bad. So in those settings, high uncertainty generally means bad outcomes. Yes?
When you say uncertainty estimation, do you mean estimating a set of where the states might be under this, let's say we fit?
I would say hang on to that question for a little bit, because maybe it'll be more obvious once I describe how we actually get these uncertainty estimates. Okay, let's continue. So how do we get uncertainty-aware models? Let's talk about some ideas about how we can train our neural net models and get them to actually tell us when they're uncertain about things. So one idea is to use the entropy of the output. So if you have a neural net, it takes in ST and AT, it outputs P of ST plus 1 given ST AT. That output is some kind of distribution. So maybe if your state is discrete, you have a softmax at the end, and you just have a categorical distribution. Or maybe it's continuous, and you, let's say, select a multivariate normal distribution as your output. In both cases, you can look at these distributions, and you can say, well, if they have very high entropy, then your model must be very, very uncertain. Why is this not good enough?
Doesn't take reward into account.
So one answer is it doesn't take reward into account. Is there a more fundamental reason why this might not be a good way to get a gauge on the uncertainty of our model?
The model might overfit and be confident, but it's wrong.
Right, so the answer was the model might overfit and it might be confident, but wrong. In fact, this is a much more fundamental issue. That's essentially the right idea, but you actually can never do this. Like, this is not a way to get uncertainty about your model. So let me explain this. Here's the picture that I had from before. And let's imagine that the blue line represents your model, and your model makes normally distributed predictions. So it takes in X, and it outputs a normal distribution over Y. Now, the optimal estimate for the variance for this normal distribution is basically the average error. And the average error for this blue line is, well, looking at the picture, it's basically 0. So this model will have an output entropy that is very, very low because its variance will be close to 0. But obviously this model is highly uncertain in many regions, as evidenced by the huge mistakes that it makes. So the variance here is low. The root of the issue is that there are two types of uncertainty, and they are very much not the same, and we can't substitute one for the other. There's something called aleatoric or statistical uncertainty, which is essentially uncertainty about the data. And then there's epistemic or model uncertainty, which is uncertainty about the model. So the picture on the right here shows a model that actually did a very good job of fitting to the data, but the data itself was very noisy. So this model incurs large error, but it's in some sense the best error it can get because the data itself inherently has noise. The data is inherently uncertain. It has high statistical uncertainty or high aleatoric uncertainty, but the model is actually a very good model. It's probably not going to get any better. So for the model in the picture on the right, we should probably trust that model, even though it gets high error. The model in the picture on the left gets very low error, but the model itself is very uncertain. So the epistemic uncertainty essentially relates to the case where the model is certain about the data, but we are not certain about the model. And you're not going to get that just from looking at the output entropy, because the output entropy for the model on the left is very, very low. And the output entropy for the model on the right is actually substantially higher. So here's a second idea. Let's try to actually estimate model uncertainty. Let's try to figure out whether we are not certain about the model. When we train neural net models with maximum likelihood, we have some p of st plus 1 given st at, and we have parameters theta. So usually what we estimate is the log probability of theta given our data, which is the same if you have a uniform prior as the log probability of the data given theta. So this is maximum a posteriori estimation, or maximum likelihood estimation. What if we instead don't just try to find the argmax of this distribution, but actually try to construct the whole distribution? What if we try to estimate the whole distribution p theta given d? Now, if we can get that distribution, then the entropy of that distribution will give us an estimate of our model uncertainty. So if our estimator says all thetas are equally likely given your data, that really means you have no idea what the model is. If your estimator says this is the only theta that can possibly explain the data set, that means that you have very high confidence in your model. And anything in between suggests different levels of uncertainty. So the entropy of this will tell us the model uncertainty. And then if you can estimate p of theta given d and you want to make a prediction, then just integrate out theta. It's easier said than done, but in mathematics land, it's easy to write it down. In actual engineering land, where we have to implement these things, this is basically impossible, but let's pretend that we're mathematicians for a second. Everything is very simple. Okay, so if we follow this route and we try to instantiate this idea with neural networks, we get what's called a Bayesian neural network. So in a regular neural network, every connection has a weight. So the picture on the left is essentially what you guys implemented for homework 1 and homework 2 and hopefully homework 3. Whereas the picture on the right shows a different kind of neural network where instead of having a number associated with each connection, you actually have an entire distribution associated with each connection. So you have a distribution over weights. And that distribution over weights is your p of theta given d. Now, representing a really complicated distribution over weights is very hard. The weights can have really complicated correlations and so on. And we'd like something tractable that we can actually implement in a computer. So we're going to do what we always do in deep learning, which is we're going to use an egregious and unjustified approximation. And one of the most egregious and unjustified approximations I could think of is to estimate your distribution over your parameters as a product of independent marginals. This is sometimes referred to as a mean field approximation. Calling it mean field makes it sound a lot more appealing because that's a term from statistical mechanics, and one might think that physicists actually know what they're talking about. So this can make us feel a little bit better about the fact that this is a rather simplistic approximation. All right, and then what do we choose for p of theta I given d? So theta I is the ith parameter. Well, we're going to choose a normal distribution, of course, because that's the simplest kind of distribution we can think of over continuous valued numbers. So we have a mean, mu I, for every parameter theta I, And we have a variance, sigma I. So you can intuitively think of mu I as kind of your expected value of that parameter, and sigma I as your uncertainty about that parameter. So if sigmas are huge, that means that you really don't know what the right parameters are. If sigmas are all tiny, that means that you're pretty sure that mu I is the right parameter value. There are a number of ways to train Bayesian neural networks with these kinds of mean field posteriors. I'm not going to go through it in detail in today's lecture. I'm actually going to describe a much simpler approach that tends to work very well, if not better. But if you want to learn more about these kinds of mean field approximations, I recommend checking out this paper by Blundell et al. Called Weight Uncertainty in Neural Networks, or the Arengales paper on concrete dropout. We'll learn more about the techniques behind these two papers, which are called variational inference, in a subsequent lecture. So that'll probably be covered next week. But today we're going to actually talk about a simpler way to estimate parameter distributions that does not involve any variational inference and doesn't involve these independent Gaussian posteriors, which is to use bootstrap ensembles. So the idea behind bootstrap ensembles is the following, that instead of trying to estimate an uncertainty for every single parameter in your network, what you'll do instead is learn many different networks. So instead of just having one network that looks at your input STAT and outputs P of ST plus 1, you have many networks. And you train these networks so that they all capture different estimates of the posterior. And then the full posterior can just be reconstructed as a mixture of Dirac delta functions. So if you have n different networks, theta 1 through theta n, we'll just say that P of theta given D is just this mixture of the theta i's. So if you can train these theta i's so that that mixture is approximately equal to the posterior, then you'll be able to use this to get some uncertainty. The intuition behind this is actually very simple. You train multiple models, and if those multiple models agree on the answer, that means you have low uncertainty. If the models all disagree on the answer, then you have high uncertainty. More mathematically, if you want to integrate out your uncertainty, you just sum over the predictions from all the models and divide by the number of models. You just average your models' predictions. That seems deceptively simple, but of course you have to actually train these models, so this is a meaningful thing to do. How do you train? Well, the main idea is that you need to generate independent data sets to get independent models. So if your models are independent of each other, then this ensembling trick works and you actually get a good posterior. But if your models are obviously all identical, they'll all make the same mistakes, they'll always agree on the same wrong answer. So that's no good. So you somehow need to take your data set and you need to get n different independent data sets out of it. And it turns out that one of the ways you could do that is by taking your original data set D and resampling that data set with replacement. So if your data set has 5 items, then you generate a new data set DI by selecting uniformly distributed integers between 0 and 4 inclusive and resampling your original data set to get 5 other data points that come from the same distribution, but they might place a different integer valued weight on the original 5 data points. So this is basically resampling with replacement. It's a little bit involved to show that this does in fact produce independent data sets, but if you do this and you have a large enough n, then you can get a good estimate for your parameter posterior. Okay, so that's at least the theory behind a bootstrap ensemble. And as you might imagine at this point, this is a lot simpler to do than doing the fancy variational Bayesian neural net. So that's what we're going to actually use. A few practical details for bootstrap ensembles in deep learning. This basically works, so there isn't really any major change that you need. It's a very crude approximation because the number of models in your bootstrap ensemble is typically going to be pretty small, right? Because every model in the ensemble requires training a different neural net. Training neural nets is expensive, so you might have maybe less than 10 models in your ensemble. So the actual estimate for the posterior is a very crude estimate. You have some complex distribution, and you're estimating with 10 Dirac delta functions. But one maybe positive thing is that this business with resampling from replacement is actually usually unnecessary because stochastic gradient descent and random initialization actually makes the models sufficiently independent all on its own. That's a purely empirical result, but you can try it out at home. You can do the proper bootstrap ensemble, and then you can try it again without resampling with replacement, and you'll probably get a similar quality posterior. Now, we can argue as to whether that means that you're getting really bad answers in both cases or equally good answers. It's sort of glass half full, half empty sort of thing. But implementation-wise, this does make our lives a little bit easier. So this immediately now gives us a method for getting a parameter posterior without too much work. Simply train a bunch of independent neural nets on your data, and then use the agreement between those neural nets to quantify your uncertainty. Any questions about this? Okay, so let's talk about how to actually use this thing. How do you plan with uncertainty? Well, let me give you a really, really simple answer. Let's say that you're doing this kind of random shooting or cross-entropy method from last week. The basic thing that you need from your model to do that is you need this function j of a1 through ah. You need some function that tells you how good is a sequence of actions. And before we saw that that function is basically the sum of rewards along the trajectory, where the trajectory is generated by running through your model. So you basically ask your f, what is going to be the st plus 1 if I take the action at repeatedly until you get a full trajectory, evaluate the reward function of that trajectory, and that's your objective value. Now you have an ensemble of networks, so you don't just have one f, you have n different f's. So what do? Well, you just average them. So you say that now my objective value is the average over all of my models of the rewards for the state sequences predicted via those models. Same actions for each one, because we have the same A1 through AH, but different state sequences because the different models might make different predictions. And this is for a deterministic model F. It's pretty straightforward to then generalize this to a stochastic model that predicts P of st plus 1 given st at. So here's kind of the more general procedure. If you have a candidate action sequence, A1 through AH, step 1, sample theta from your parameter posterior. So if you have a bootstrap ensemble, simply pick one of your n parameter vectors. If you have a Bayesian neural net, sample from the normal distribution over each parameter. So get your theta somehow. Step 2, at each time step, sample your next state from the next state distribution induced by theta. So sample an entire trajectory of states. Step 3, sum up their rewards. And then step 4, repeat steps 1 through 3 and accumulate the average reward over all of your sampled thetas and all of your sampled state trajectories. And that'll give you the expected value of the reward for a given candidate action sequence under stochastic models and distributions over weights. And this is something that you can then use in place of that planning step in model-based RL version 1.5. Now, there are other options besides this kind of sampling business. You can do some fancy approximations to state distributions using moment matching. You can have more complex posterior estimation with Bayesian neural nets and so on. We won't cover that in today's lecture, but keep in mind that this is kind of just merely the simplest way to estimate expected reward. There are also many others, and some of the papers that I'll reference towards the end will tell you more about that. All right, any questions about this procedure? Okay. So let me give a few quick examples, and then we'll take a little break. So this is a paper called Deep Reinforcement Learning in a Handful of Trials Using Probabilistic Dynamics Models that was basically trying to deal with the problem that I mentioned before. So before we had our model-based thingy getting up to about 500 reward. Once we incorporate bootstrap ensembles, we get to above 6,000 reward after the same 10 minutes. So here, 10 minutes gets to 500. Put in bootstrap ensemble, gets to above 6,000. So the uncertainty estimation does actually make a pretty big difference for these kinds of problems. Here's a cute video. This is also from Anusha's work, so you can go to her office hours and ask her about this. This is a method based on roughly the same general principle, running on a real robot, trying to get this robotic hand to play with the bounding balls game. So the robot arm puts the things in the hand, and then the hand tries to practice spinning these things around. And it takes a couple hours to do this, but this is essentially using kind of a fancier version of model-based RL version 1.5. So 0.5 to 1 hour in, it can kind of keep them in the palm a little bit. 1.5 hours in, it can make about half a turn. And then 2 hours in, it can actually do a pretty decent job of making a full turn with this little game. So this stuff actually does work in practice, and this is all trained on the real robot. Okay, if you want to read more about this, this is a kind of a classic paper by Mark Dusenroth called PILCO that it doesn't discuss deep reinforcement learning, but it does discuss using Gaussian processes for uncertainty-aware reinforcement learning. So if you want to get kind of a deeper dive on that, check out this paper. More recent papers, this is the paper that I got that learning curve from. This is the more recent paper using the bootstrap ensembles. And these are a couple of other more recent papers that study the effect of uncertainty for model-based estimation of value functions and Q functions. So if you want to dig a little bit more into these topics, I would recommend checking out these papers. So at this point, we'll take a short break. So we'll be back at 11:04, let's say. And then we'll talk about images and latent space models. So see you all at 11:04. Just because sometimes I turn on the projector and I'm worried that they might not hear me when I do that. Okay. So then if I just stand here, it's okay.
If you ever need to write the board, then I'd just want to speak louder.
Yeah, I think I can probably avoid using the board for today. It would be nice to get it fixed for next time, but this is good.
Yeah.
Yep.
I have a question. So it seems like the mean and like the expected reward. It seems like the issue here is that like the function of like the expected position, like expected trajectory is not equal to expectation if like it's not equal to this, right? This is what we estimate, and this is what we get when we. But like, how does having like multiple models? It still seems like we're estimating this. Like,
that's not the only issue. The bigger issue is that. Your model just makes incorrect predictions for some action sequences. So
an expectation is right. An expectation trajectory is correct.
If you have the full posterior over parameters, yes. But if you just train a single neural network, like you have variance in machine learning, right? You take the same size data set, sample it multiple times, you get different predictions.
Sure. Yeah.
So that means that the expected value doesn't. The expected value from a single model, from the maximum posterior model, doesn't necessarily give you the correct answer. So it's not just about moving the function aside the expectation, it's just because your model is incorrect.
Okay.
Because you're querying it with inputs that are outside of the distribution of inputs that it's trained on.
Okay. Sure. Okay.
I'm still confused about the image in Anusha's picture. Okay. So when we have this PS dash slash ST+1 slash STAT come out, how are we implement this? Is it?
Yeah. So the way that plot was generated is that for the first 500 steps, you train P of ST+1 given STAT,
Yes.
and then you use it to plan.
Okay.
Then, after 500 steps, you take all of your data that you've collected so far for every state, you generate a plan, so you get a state and an action, and then you just do supervised learning to map from states to actions.
So this policy only used at that single step, and for the others, it's all the previous thing we're talking about.
Exactly.
Okay,
exactly.
so only one step.
Yeah.
Thank you.
I have a question about the, so there's like, seems to be this trade-off between expressivity and the fact that you have, like, there's a small number of samples you're going to do correctly. Have there been any models exploring how to do like maybe similarly to like how the human brain learns in critical periods, like breaking up a task into subtasks such that you have a period where there's rapid learning and expressivity within a certain subdomain, and then you move to another one and then you integrate. Because it seems like that's a pretty good way to,
Not really model-based RL. I can point you to something that's maybe like overly technical that looks a little bit like this. So people have studied whether critical periods exist in regular supervised learning for regular neural nets. And there is a little bit of, there's something going on there because a randomly initialized neural net with like close to orthogonal weight matrices tends to learn very rapidly, and after it's been trained for a while, then it learns a lot less rapidly because kind of the intuitions that the weights have sort of found their comfortable niche, and they don't want to leave that niche. So if you search for critical periods in neural nets, you will probably find a bunch of papers that study this question. I don't know if anybody studied it in the context of RL, but certainly in the context of supervised learning, that's actually a thing. All right, let's resume. So in the last part of today's lecture, we're going to talk about model-based RL with more complex observation spaces. So far we've talked about half cheetahs, not even full cheetahs, and half cheetahs have a small number of dimensions. What happens if we want to do model-based RL with much more complex observations, like, for example, image observations? Maybe we want to play Atari games with model-based RL, or maybe we want to control robots using cameras and things like that. We could still try to learn an f of SDAT that gives us an ST plus 1, but this can get a little tricky if ST and ST plus 1 are represented by images. What is hard about this? Well, you have high dimensionality. So before, for the cheetah, S was maybe like 18-dimensional. Now it maybe has thousands of dimensions. You have a lot of redundancy. So like the yellow pixel over here might move very similar to the yellow pixel right next to it. So even though they're different entries in the state, they're kind of redundant with each other. And you might have partial observability. So it might be that both for the robot case and for the Atari game, the image doesn't actually tell you everything about the underlying state, just like that example in the beginning of the course with the car blocking the cheetah and the gazelle. So maybe one of the things we could do, if we want to get model-based RL to work with complex observations, is go back to the model that we had before with partial observed MDPs and treat those images as observations of some unknown underlying state. So this is the picture that we had at the beginning of the course, where we have states. States together with actions give rise to next states, and states also give rise to the observations, which is what you actually get to see. So the pixel image of the Atari game is not actually the state of the game, it's an observation produced by the underlying state. So we have some dynamics, but the dynamics are on states, and we don't actually even know what the states are. So perhaps we can separately learn P of OT given ST, the function that generates observations as a consequence of the underlying states, and P of ST plus 1 given STAT, which is the transition dynamics on the unknown underlying state space. And this might be nice because the P of OT given ST has to model something pretty high dimensional, but it's not dynamic. So it's basically just like the function of how the position of the paddle for breakout generates the pixels of the paddle. So it's dynamically quite simple. And then P of ST plus 1 given STAT might be much more complicated because of the dynamics, but it's probably pretty low dimensional. So if you can somehow pull out a state from these Atari images that reflects roughly the position of the paddle, maybe modeling the dynamics in terms of that is a lot easier. So that's the high-level intuition for why we might prefer to model systems with high-dimensional observations with these latent state space models rather than directly predicting the next image. Although we'll see at the end of today's lecture that maybe that's not always the case. But let's go with this for now and see where that leads us. So if we want to learn this kind of latent space or state space model, we need to learn P of OT given ST. That's our observation model. We need to learn P of ST plus 1 given STAT. That's our dynamics model. And crucially, we only observe OT. We don't actually observe ST and ST plus 1. We don't even really know what they are, so we have to learn them as latent variables. If we want to actually use this for control, using something like the model-based RL version 1.5 algorithm, we actually need one more thing. This won't quite suffice. Can anyone think of what other distribution we might need to learn? Yeah.
We need to figure out probability of ST given OT.
We need to figure out probability of ST given OT, right? So we only observe O's, so we need to somehow invert that. We'll see that in a second. Is there anything else that we need? Well, this is a little subtle, but we need to evaluate rewards for these things. Rewards are typically a function of states. So before, when we were just predicting states directly, this wasn't really a problem because typically you kind of know what your reward function is as a function of the state. But usually if you're doing control from images, like for example in the little robotics case here, it's a little difficult to get a function that looks at image pixels and gives you a reward value. So typically when we learn these latent state space models, we also need to learn the probability of the reward given the state in action, because these states are not actually given to us, they're latent variables. So we might need to also hang a little reward node off of the state in action and learn that too. So that's our reward model. It's not a big deal, but it's just something to keep in mind. Okay, so how do we train this whole thing? Before, when we had a standard fully observed model, our training was basically maximum likelihood. So I typically wrote it as minimizing squared error, but squared error is simply the log probability under a normal distribution with unit variance. So at a high level, all of the model-based RL methods that we saw before were basically doing this. They were all doing maximum likelihood training. Maximize the log probability of ST plus 1 given STAT for all STAT ST plus 1 tuples observed in the data. And if you represent P phi here as a normal distribution, then this corresponds to minimizing squared error. If you represent it as anything else, then it's just whatever your parametric distribution class is. So this is what we were doing before for all the algorithms that we've covered. But now we're in a little bit of trouble because we don't have ST plus 1 and ST. So now we need to do something a little bit more complicated. We need to use an expected log likelihood. So we still have our log P of ST plus 1 given STAT. We now also have our log P of OT given ST, and potentially even our reward model, RT given STAT. But since we don't know what ST is, we need to take this log probability in expectation under the posterior, under P of ST plus 1, given your full sequence of observations and your full sequence of actions. And that's what makes the training for this quite a bit more complicated. So we'll talk about this a bit more in the next slide. So to train your latent-based model, you need to somehow be able to calculate this distribution, P of ST plus 1 given, and ST, given the sequence of observations and the sequence of actions, sample from that distribution, and then you can evaluate your expected log likelihood and take its gradient. So typically the way that we do this is by learning an approximate posterior. So the exact posterior over here is typically intractable if you have very complex dynamics and very complex observation functions, like neural nets. But you can calculate an approximate posterior, which we'll typically refer to as Q. So if you see me write Q of something, that refers to an approximation of the posterior rather than the true posterior. And you can have many different kinds of approximate posteriors that are conditioned on different parts of your evidence. So you could, typically we refer to this as an encoder. So you could, for example, have a full smoothing posterior, which is conditioned on all the observations and all the actions in a trajectory. Or you could have a very simple independent posterior, just Q of ST given OT. So when I say full smoothing posterior, I mean that it's conditioned on everything. And this I'm going to call the single-step encoder. Now, what's the trade-off between using different kinds of posteriors? Well, the full smoothing posterior is the most accurate because the thing you're trying to approximate is this, so it's conditioned on the same stuff. So if you have a very expressive distribution class and you condition on everything, that's going to be the closest to the true posterior. The downside is it's also the most complicated to implement. If you want to output a distribution over ST and ST plus 1, condition on a whole sequence of images, you need to read in those images somehow, maybe you have a big RNN or something. So that's a pretty complicated model to set up. The single-step encoder is the simplest. It's very easy to set up. It's just a convnet that reads in an image and outputs a state vector. But it's the least accurate because it's not conditioned on the same stuff. It's not looking at the full observation sequence. And especially if you have partial observability, maybe you can't get a very good estimate of your underlying state just from looking at a single image. So it might not be a very accurate posterior. Now, you also have to train these posterior distributions somehow. We'll discuss how to train Q-psi later when we talk about variational inference. We'll talk about that next week. Today, we're going to actually describe a much simpler way to do this that doesn't work as well, but it's still pretty good and can allow us to implement this stuff without worrying too much about fancy statistics. So to do that, I'm going to focus on the single-step encoder because that's the simplest, and I'm going to then make it even simpler. But next week, I'll make it more complicated again, and you'll see how we can actually get really complex posteriors, including things like the full smoothing posterior. But let's go with just a single-step encoder for now. So that's Q psi ST given OT. If we can obtain Q psi ST given OT, then what we can do is we can take our expectation with respect to ST distributed according to Q of ST given OT, and ST plus 1 distributed according to Q of ST plus 1 given OT plus 1. So basically encode your current observation, encode your next one, and then maximize the log likelihood of your dynamics between them and the log likelihood of the observation. And what I'm going to discuss here is actually a special case where Q of ST given OT is deterministic. So I have it written here as a distribution, but we'll just say, for now, it's a very simple distribution. It's a special case. The stochastic case requires variational inference, which will be discussed next week, but the deterministic special case is basically just a delta function. It says probability of 1 assigned to ST equals G psi of OT, and 0 to everything else. Or equivalently, ST is equal to G psi of OT. So it's a deterministic encoder. You just have a neural net, G psi, it looks at an observation and tells you what state it thinks this observation corresponds to. This is a very, very simple choice for the encoder. It's not a very accurate choice, but it is a very, very simple choice. And because it's deterministic, expectations under deterministic functions can be obtained just by plugging in that function into the stuff inside the expectation. So I can simplify my expected log likelihood to just be this. The log probability of G psi of OT plus 1 given G psi of OT comma 8t plus the log probability of OT given G psi of OT. So the second term is essentially a kind of autoencoder term. It says if you encode OT with G psi, you should be able to decode it back out, which means that your state should capture whatever information is contained in the observation. And the first term just says you should have dynamics on your encoded observations. So this is a latent space model with a deterministic encoder. And this thing now you can just train entirely with backpropagation, just implement this likelihood, and then optimize it with respect to phi and psi jointly. Everything here is differentiable. You can train it with backprop. Does anybody have any questions about this approach for training a latent space model? Yes?
Why do both the probability distributions have the same parameters, just phi?
Right, the question is, why did I write p phi here and p phi here? Because I was going to run out of Greek letters. Yeah, so you can pretend they're different. This becomes a little bit more meaningful later on when we talk about variational inference, when we want one vector of parameters for all the p's and a separate one for all the q's. Any other questions? Okay, so we can train up these kind of latent space models, and then we can use them for control. How do we use them for control? Well, just take your current observation, encode it, get it the corresponding state, and then do the same thing as before. So now we have our function st equals G psi of OT. So it's this represented by that dotted curve. We still have our reward model, so we probably want to add that too. So we want to learn the reward condition on the encoded observation. The reward can depend on the action too if you want. So we have our latent space dynamics, our image reconstruction, and our reward model. And that gives us all the pieces we need to implement model-based RL on complex observations like images. Many practical methods that use this recipe actually use a stochastic encoder to model some uncertainty about the encoding, which is very important, especially in partially observed settings where more than one state can correspond to the same observation. So it'll be more apparent how we can train that next week. But for now, let's stick with these deterministic encoder models. Here is a version of model-based RL 1.5 modified to include this latent space model. So step 1 is just the same as before. Run your base policy, which now depends on observations, to collect a set of tuples O, A, O prime. Step 2 is learn your dynamics model, your reward model, your observation model, and your encoder using that data set. Step 3 is plan through this model to choose your actions. Step 4 is execute the first planned action and observe the resulting observation O prime. Step 5, append it to your data set. Go back to step 3, so you choose a new action every step. And then every n steps, retrain your dynamics model, your reward model, your observation model, and your encoder. And they're all trained together with backprop. So that gives us a complete algorithm that we can actually use. Yes?
Do we assume the probability distributions are Gaussian?
Question, do we assume that the probability distributions are Gaussian? You can use whatever distribution class you want. You can even imagine using deterministic states. Typically when people do this, they do use Gaussians for the dynamics. For O given S, they use independent Gaussians over all the pixels. So it's a little bit of a simplifying assumption, but it makes it very convenient to train. And then for the reward, you train it with squared error, which also corresponds to a Gaussian. Yeah. But you don't have to. Any other questions? Yeah.
For the function that approximates the state given the observation, do you have to make some assumptions about the dimensions of the state space?
Yeah, so the question is, do we have to make some assumption about the dimensionality of the state space? So we don't know anything about the state space. We do have to pick its dimensionality, and typically that's chosen by hand. If you have some knowledge about the system, you might be very tempted to select the underlying dimensionality of that system as your dimensionality for the state. So if you know that you're controlling a little pendulum with 2 degrees of freedom, maybe you pick the latent state dimensionality to be 2. That's not actually always the best idea. Sometimes you might want to select the dimensionality to be a little larger than the true underlying dimensionality to give the model a little bit more freedom to actually find a good solution, because even like a 2D system might be easier to embed in 3 or 4 dimensions. Any other questions? Yeah.
How is it related to Kalman filter?
Mm-hmm.
If you use Kalman filter to find the
Yeah. The question was, how is this related to a Kalman filter? So this type of model is, the actual structure of the Bayes net is the same as a hidden Markov model or a Kalman filter. The difference is that a hidden Markov model has states and observations that are all discrete and typically uses tabular representations. And a Kalman filter has states and observations that are all continuous and uses linear Gaussian parameterizations for everything. So if you can get away with linear Gaussian parameterization, this is all very easy. You just train it as a Kalman filter. If you can get away with tabular representation, you train it as an HMM. But if you have high dimensional things like images, probably neither of those will really work. So then you have to train it in some fancier way. Yeah, in fact, actually, one of the papers that describes a model of this type is literally called Deep Kalman Filter. Any other questions? OK. So let's look at a few examples of papers that have done some variant of this. This is a paper called Embed to Control by Water et al. In this paper, what they do is they train a latent state space model, similar to the architecture that I described, only they have a stochastic encoder instead of a deterministic encoder, but otherwise very similar idea. And what they're going to do is they're going to control a few different types of low-dimensional systems, and they'll use a very low-dimensional state space embedding so they can visualize it. So here's a video. Their first task is a little 2D navigation task where you basically are navigating in a plane with these obstacles denoted using the white dots. And what they're showing on the left is the true state space, and on the right is their embedding as learning progresses. So you can see that as learning progresses, it sort of embeds, kind of unfurls the state space into a geometry that more or less matches the true one. Here's a more complex task. This is a pendulum swing up. So there's a 1 position and 1 velocity degree of freedom. And their embedding is actually here in 3D. It, again, kind of unfolds the state space of the pendulum into this cylinder shape, which seems like a reasonable shape for a pendulum. Here's what the pendulum actually looks like. The images are very simple. They're just black and white images. On the left, you can see the real image, and on the right is the prediction made by their model for 1 step forward. So the way they get that prediction is that they encode the current image, predict 1 step forward, and then decode. Here's the same thing for a little cart pole balancing task. So again, it's a black and white image, slightly more complicated than before. And you can see the 1-step prediction gets a little blurrier, but basically has the right idea. And here's another task. This is a little 3-link arm. It's a kind of this very muscular robot arm, and it's supposed to reach for different locations. So here they're having it reach to some location. OK, so that's kind of some state space models with images. And for them here, the underlying control algorithm is actually model predictive control with the same LQR procedure that was used in with the little hopper and humanoid type robots that I showed before. So this is actually using LQR for control. Here's another kind of more recent paper. This is called SOLAR, Deep Structured Latent Representations for Model-Based Reinforcement Learning. Here, the graphical model is a little bit more complex. There's actually a prior on the dynamics themselves to keep them a little bit more well-structured. And there's some evaluations on some real-world robots. So this is a little Sawyer robot stacking some Lego blocks. And this is a robot learning to push a cup to a little coaster. And you can see one of the authors of the paper, Laura, here. She's pressing a button on the keyboard. And what she's doing there, she's actually directly giving rewards to the robot. So this algorithm actually learns fast enough that you could sit there. In this case, I think it was for about like 30 minutes or so, and just push the button to give it rewards. And then it uses that to train its reward model, the P of R given S, comma A. So here's a little illustration of that method. First, there's some data collection. So it's moving the arm around, mostly randomly, collecting data to train up that state space model. And in the top left corner, you can see what the robot is actually seeing through its camera. Then it has a few different tasks. All the tasks can share the same model. So here it's going to try to iteratively learn the task. So this is basically that version 1.5 algorithm where it tries the task using the latest model, collects some more data, updates the model, and so on. And for each attempt, it's using MPC. And you can see it gets better and better. And the little picture on the left shows the reconstruction. So the top one is the real image. The bottom one is if you encode and then decode, just to make sure the state space is really capturing all the necessary factors of variation. So the bottom image should look similar to the top image if the state space captures all the important factors of variation. Okay, so they figured out how to stack the Lego blocks successfully from images by using the state space model. All right. Now, so far, all of the methods for model-based RL from images that we've talked about basically operate on this idea that we're going to train an encoder, either a deterministic or a stochastic encoder, that takes in the image and outputs a state embedding. And I said at the beginning that maybe we don't want to directly learn to predict next image from current image because maybe it's high dimensional or maybe it's redundant and so on. But we could give it a shot. So we could sort of ignore the good advice of the wise experts and just do the obvious thing of directly learning P of OT plus 1 given OT-AT and forget about states altogether. And that can actually work decently well. So there are a couple of papers that have done this, and I'll show some videos from this, but the high-level idea in all these cases is that you have some really gigantic model that takes in an image, typically does some kind of convolutional RNN type thing, and just directly spits out the next image. And you just apply this repeatedly to generate a whole sequence of images. It's essentially a video prediction model. So you can train up these video prediction models, and then you can ask them to make predictions for different action sequences. So what you're seeing here at the bottom are each row starts from a different image. So all the sequences in the top row start from the same image, and all the sequences in the bottom row start from the same image. But they're all conditioned on different action sequences. So they're all kind of different what-if predictions. So all the images in the top row show if you start from the same place, what if you move the arm to the left, what if you move the arm to the right, what if you move the arm down, etc., etc. And you can see that the predictions for the different action sequences are somewhat coherent. The arm moves in the right direction, and if it contacts an object, it moves that object in roughly the right direction, and also for some reason turns into a huge blur. Why does it turn into a blur? Well, because the future is uncertain, and if you have multiple possible futures that you superimpose on each other, then you get a blur. So the future is uncertain, but somewhat reasonable. One of the issues that you have to contend with is if you take this approach is that you then have to somehow figure out how to tell this algorithm what you actually want it to do. You can either learn a reward model like before, or you can come up with some other interface to the system. One interface you can imagine adopting is one where you actually just tell the model how to move pixels. You say, well, whatever is here under this red pixel, move it over here. I don't care what it is, just whatever is here, move it here. And then the algorithm can use the underlying video prediction model to figure out which action sequences move the pixel in the right way. So the little heat maps you're seeing at the bottom basically denote the model's prediction about where the designated pixel in red will move. And then you can get a robot to actually do this. You can get it to reach out and grab a stapler, move it to a desired location, and so on. So this is without even going through the underlying state space modeling. OK, well, so that's it for model-based reinforcement learning without policies. On Wednesday, I'll talk about model-based reinforcement learning where we want to actually learn entire policies to kind of close the loop. And then next week, I'll talk about variational inference. So see you all on Wednesday.